Hello, my name is Brad Schofield. I'm section leader for the Automatic Control and Safety section in the Industrial Controls group at CERN. So I'll share some experience again with model predictive control, this time for industrial control systems. So I'll just briefly introduce one of the use cases that we've been looking at in the last couple of years, which is energy optimal control of air handling units. So looking at energy optimization, basically. Very briefly introduce MPC because it's already nicely been done. And then focus a little bit more on what we do for the implementation, and then a bit more again on where we're going in the future with this, because we've done a pilot on a single installation, but we really want to do many installations to get real energy savings. And there, we're going to look a little bit at machine learning, but maybe not in the way that you might expect. So it's a bit different. So the case study that we've looked at in the last couple of years is energy optimal control. For CERN, we use a lot of energy, as you might expect. It's over a terawatt hour per year. A few years ago, we had this energy crisis, and that was really causing some concern, and this got a lot of focus. In general, we want to try and focus on efficient operations, so focusing on numbers like how much energy you need per a given amount of physics data. And we want this to improve with high Lumia LHC, and obviously if we go to FCC, we want it to get even better then. One of the nice ways you can do this on the cheap is to make your controls better. So one area that we've looked at, which is a user of energy, not the biggest, but it's quite big, it's around 100 gigawatt hours a year, is the cooling and ventilation systems. So here we have like cooling towers, cooling primary water that's used by the cryogenics, cooling equipment, and then we do HVAC for a lot of technical buildings. So for the HVAC, where you have air handling units, this is a typical kind of multivariable control problem, which is not really a regulation problem. It's just keeping temperatures and maybe humidities in a certain range with a lot of actuators. So typically you have like a variable speed-driven fan, you have cooling heating coils, and you have some dampers to control airflow. And you're just interested in keeping things within ranges rather than a specific set point. Classically, you'd solve this, for example, with like a cascaded PID. When you do this, now you're saying I have a regulation problem. So you have to choose some set points, and then your optimization that you can do is kind of restricted to setting those set points. And if you do this dynamically too much, you can have kind of odd dynamic effects in your closed-loop system. But what you'd prefer to do is to do something that explicitly expresses your control problem as constraints and ranges of allowable temperatures, let's say, and also explicitly take into account energy consumption. And ideally to take into account disturbances which can be present or even future. So for something like an HVAC system, you have very good predictions of future disturbances in the form of a weather forecast, say. So we'd like to take that into account. So that leads us to MPC. I'll go super quick through this. I don't think many of you need the background here. But MPC is basically giving you a set of control actions, so not a control law, but control actions over a discretized fixed horizon that minimizes some costs and respects some constraints. And to do that, you necessarily have to have a dynamic plant model of some kind, which has to be decently good. And this gives you an optimization problem to solve, and then you apply the first in the sequence, and then you do everything again at the next time step, which gives you the feedback. For the air handling units, I mean, the details of the equations don't really matter. We've already had a nice presentation of the way MPC works. But what you basically have is a cost function, which in this case is dominated by energy consumption, and then some bits and pieces later that don't really matter. And when you're doing control, it's always subject to the dynamics. So it's subject to satisfying your equations of the dynamic equations given by these Fs. Then you have some constraints, which could be hard constraints, like on actuators, or soft constraints with the slack variables here on states. So you don't get infeasible problems without when you don't need to. Then you can have rate of change constraints as well. And obviously, you have to start the initial value problem with where you are now. And then you have the slack variable as well, just to deal with the infeasibility. So the models are pretty simple that we use for this. So the kind of first order mass energy balances that you get, they're not that hard, but you have to parameterize them. The same with the models for the energy consumption. But they're nonlinear, and they're actually bilinear in the control variables, so they're not easy to linearize. So for the implementation of this, what we did is to use a framework called Casadi. So I'll talk a bit more in a second, because this gives you since it's bilinear, you can't really linearize sensibly. So you end up with a nonlinear program to solve. This is not something you want to do on a PLC unless you really want to suffer. You want to use a framework that'll do this with some libraries and do it somewhere else other than the industrial controller. So we use Casati, we solve it on someone else's computer, in the cloud or a SCADA server, something like this, and communicate back to the PLC with OPC-UA in this case. We also keep the classical controls as a kind of backup, and you can switch sort of seamlessly by tracking the PIDs to what the MPC is doing the best they can, and switch back and forth. So Casati, just quickly, is a framework fundamentally for algorithmic differentiation. So you basically build these computational graphs. You have a symbolic framework and then computational graphs. And this is kind of, if you know about training neural networks, you can do the same thing with this as you do there. So you basically trace back partial derivatives through these graphs to figure out how you should adjust parameters, or in this case, control variables. Casati integrates with state-of-the-art numerical solvers and integrators. So it doesn't implement them, but it integrates with them. So it's really well suited to optimal control problems. And for an MPC problem, even of this kind of size, it's a few lines. Like the core code is really small, and it's got interfaces for Python and C++ and MATLAB. So it's quite compact to use. Very quickly about the deployments. I mentioned this at the last ICALEPCS, so I'll just fly through it now. There's a big technical building. This is the LHC under here. This is point 1, so the Atlas. It has 2 air handling units. And we deployed one a couple of years ago, 2023 on one side. And then earlier this year, we renovated the controls and we put MPC on both sides. And then a couple of slides just to show that it works. So it can use like future values of outside temperatures to do something now. When you have colder outside air at nighttime, typically, you can pump it in and cool it down. So the energy savings potential looked pretty good. We're still running it as a pilot. We still haven't really tuned it on the real plant. We're using like the old parameters. We haven't changed it yet, but it looks like some good energy savings are possible. But if we really want to cut down on this 100 gigawatt hours, we need to scale it up. So we don't want just one MPC installation on one HVAC. We need to do it for the hundreds of installations that we have. So there we come to the last problem of finding models out of historic data for many installations. And we're going to see if we could use machine learning to do something like that. So yeah, the MPC part, the communication, the implementation, that's kind of solved. But we need to be able to quickly and with not too much engineering effort find decent models from data. At CERN, we have loads of data from the existing control systems where we have an existing installation. So very quickly, looking at the model that we have, you have something like this, discrete time model. You could say, initial step, let's replace that with a neural network, which we train from data. But this is where I want to deviate a little bit from the path. We need to remember that the real dynamics are continuous. So your next state predictor is really a solution to an ODE or a DAE generally, where you have some continuous time dynamics. And for most things, certainly for like an HVAC system or cryogenics, something like that, we know what the physics are. So we know what's inside this F structurally. You just don't know what the parameters are, so the theta here. And if you use a neural network in this way, you're throwing away that structure. Plus, in some kind of esoteric sense, you have to train this network to integrate as well, which feels like kind of a waste of effort. So if you say, let's keep the ODE solution, there's been work on that on the AI ML side for the last few years to do something called neural ODEs. So you're basically training a network to learn the right-hand side of your ODE, your vector field, basically. This is kind of nice. It means you have to train it through a solver, which is interesting. Touch on that in a second. And this is good, but it still means you're throwing away the structure that you generally know. So what you want to, or what I think we want to do, is to go back to say, I just want to learn my theta parameters, my physical parameters from this data in the same way that I would train a neural network. So if I can train a network with 1 million parameters through an ODE solver, why can't I find a load of physical parameters from my real model, let's say? So you can kind of start doing this by thinking of how you train a neural network. So you're minimizing a cost function between your prediction and your data. If we go back to optimal control a little bit, we can always say, let's add to that cost function a Lagrange multiplier times the constraint of our dynamics. And if you do a couple of pages of math, you can find that you can actually find the gradients of that cost function with respect to your physical parameters, not neural network parameters, by solving another ODE for your Lagrange multiplier. So it's like a lecture in there, but it's kind of cool and it works. So you can say I have a predictor, which is basically just forward solving a initial value problem. Then you go, what's my cost, the gradient, my cost function with respect to parameters with that trick. And then you can use any of these flora of gradient descent methods that's coming to update your state. So we're using what's coming out of machine learning to give us nice gradient descent methods on this. So then, as far as I got with this, is just to try it on like a toy example, which is really simple, but also weird enough to be interesting maybe. And it seems to work. So you start off with some set of parameters, you let it go through your time series data, and sometimes after a while, it will converge to something that makes sense. So the next step is to really try this on the historic data that we have, see if we can fit some of these first principle models. And then you could even consider, if it does work, that you can fit parameters to models of like component-based models. So something like a Modelica model, Ecosym Pro is something similar that we use at CERN. So you could have like a component-based model that maybe has hundreds of parameters, but then just let this algorithm chew through this and through the historic data we have and try and fit some of those parameters. With the AD stuff, you can go a little bit further with the MPC as well. You can ask the question of what's the sensitivity of my MPC solution to my model parameters? So you can get an idea of what model parameters are important for the MPC solution, at least in a numerical way here. And we'll get you a little bit in the sort of robust MPC direction. Yeah, so to summarize, for us, for industrial controls, so not fast systems, it's quite nice to use something like Casati running somewhere else, communicating with OPC UA to the PLCs. Obviously, it works at the speeds you need for industrial controls, maybe not faster. But the kind of remaining problem to scaling up is to identify these model parameters from many installations without spending months of work on each one. So we're going to see if these things actually work in the end. We have a new PhD project starting up, so we'll see where that goes. Thanks. Any questions?
That was a nice presentation. Can you comment on the historic data part? I'm curious, how far back do we need the data? And usually, the older the data, the less data we have, right? We are only saving features for the older data, and we have latest data. So that's the first question. And I have other part, the same question. Are there any gaps from the data you have and the learning methods you want to apply? So, yeah.
So at CERN, we're maybe a bit particular and a bit spoiled. So whenever we have a new control system, the control system data is saved in our long-term archive. So it's kept basically forever, at least for the horizon of CERN. So yeah, for that, we don't have a problem. The data is there. So the second question, you have some slight issues where you have data compression. So it's obviously dead banded and filtered in various ways, which can mess up the data a bit. But the technique that I'm looking at here is quite robust to that. Like you don't need uniquely or uniformly, sample data, because you're just integrating between whatever data points you have. So that if it's a minute or 5 minutes, you don't care, because you just do one initial value problem over that horizon to get your next one. So basically, yes, for existing installations, yeah, we have in the historian the data we need to do this. Yeah, whether it works or not, I don't know, but we have the data.